Hi, my name is Kelly Aitken. I'm the Business Development Officer for the Mdt project, which is a European Regional Development Funded project based at the University of Central Lancashire's Burnley campus. We provide up to 150 hours of fully funded support to help Lancashire-based manufacturing SMEs adopt Industry 4.0. Our team specialises in data visualisation, data analytics, IIoT, the Industrial Internet of Things, as well as robotics and automation. This video is part of a series of videos designed to give you a more detailed insight into each of these subjects. Please contact me using the details on the screen to discuss how Mdt can help your company. Thank you for listening.
Hello and welcome back to the second part 2 video of process mapping. My name is John Pinder and I work for UCLAN as a digital manufacturing project engineer, where I mainly assist local manufacturing SMEs with the implementation and project management of Industry 4 projects. And these usually involve everything from advanced robotics and automation to data analytics using artificial intelligence. If you can remember last time, in the first part 1 video, we looked at how to process map and we looked at some 2D discrete event simulation in order to look how we could improve the process. But now we're going to look in part 2 video more into value stream mapping and how we can use 3D event simulation to help us along with some technology improvements. So if you've ever heard of the term value stream mapping or value stream, it refers to all of the activities required to transform a customer request into goods or a service. And it builds upon the previously explained flowcharting method by adding information about the process to a flow diagram. The value stream map contains a visual representation of material and information flow, unlike the current state activity map which we looked at previously, which was an Excel spreadsheet. And because of this graphical way of representing this information, it provides a clearer understanding of the process by allowing users to visualize the process, recognize sources of waste, and eliminate the non-value added activities. Improvements can then be made based upon the information provided by the value stream mapping process using techniques such as the 5 W's and 2 H's. And then it enables users to reduce costs, inventory, lead times, whilst also improving quality and productivity. So how do we actually map a value stream? Well, we use the same steps for creating a process map or flow diagram as we did in the previous video. However, this time, extra details such as cycle time, changeover time, uptime, process activities, operator self-inspection notes, and even specifications are also recorded. It allows you to accurately specify the value desired by the customer, and you go to where the action is taking place and identify every single step in the value stream. You collect current information by walking along the actual pathways of the material and information flows, and this may require several walkthroughs. You begin with a quick walk along the entire value stream and continue with subsequent visits to gather more detailed information if required. Often, process mapping is easier done if the process is worked backwards, as this reduces the probability of missing an activity because it takes place more slowly, without jumping to the conclusion of, I know what's going to happen next. It's best done with a pencil, paper, or stopwatch, and although many process mapping computer programs exist, it's often difficult to get them right to where the action is taking place. You can, of course, use tablets, but obviously a pen and paper is probably going to be best. After all, the point of creating this map is to understand the flow of information and the material, not in creating the map itself. So let's have a look at some of these extra pieces of data that you may include in a value stream mapping. So the number of employees or workers. So it may take 2 workers to lift a batch of panels, it may take 1. This is worth noting down. The output, so how many parts per hour are actually being produced. Shifts, the number of working shifts that are currently in use. And process waste, this is an estimated percentage of waste for a process. The cycle time, this is the actual time taken to complete a part, product or service. Uptime, machine either fully operational or is ready to perform its intended function. Changeover time, the time required to convert a line or a machine from running one product into another. So after we've documented the process using the previously explained current state activity maps and flowcharts, We can combine these into a more complete and easy to understand value stream map, which represents the current state of production before any improvements have been made. Beginning from the top, we can see that the information flows where the customer orders around 20 products a day, and this information is combined into a daily order and fed into the Enterprise Resource Planning System, or ERP system for short. Depending upon how sophisticated your ERP system is, and the warehouse management system may then combine this information into weekly orders and monthly forecasts for ordering the required parts automatically from your suppliers when the inventory is running low. In summary, the orders are fulfilled daily and new materials are delivered on a weekly basis. Now for the material flows. The Production Supervisor, or Material Requirements Planning System, or MRP for short, plans and schedules where the materials need to be at any one time to complete the process. As you can see, this is performed on a daily basis for all of the processes. This manufacturing process of assembling insulated panels for refrigerated vans has 10 key processes. These processes are described in sequence with a human symbol used to show how many people are used for the process. In addition to this, there's also an inventory triangle which shows the amount of parts either completed or waiting to be processed at any one time. Below the process, you can see the additional information we talked about on the previous slide, and finally the lead time ladder at the bottom of the diagram. Now this lead time ladder is very important as it shows you the total lead time at the top for each of the processes. In this particular case, we can see that the materials have been sat around in the store for just over 5 days, and the first value adding process of cutting the material actually only takes 3 minutes to complete. The flat panel sub-assembly takes about 20 minutes to complete, and the vacuum curing takes just 10 minutes. When you add all of these value added times up and divide this by the total lead time, you end up with an easy to understand process cycle efficiency number, or PCE value. As you can see from this calculation, we had a total of 91 minutes of value added time and a huge 8.3 days of total lead time, which resulted in an extremely low PCE value of 0.76%. Clearly this process needs to be improved, and if you look again at the left hand side of the map, you'll notice that we have an inventory sat around for nearly a week with no value being added to it. We can use these Kaizen symbols to represent identified problems that can be improved upon. So when your value stream map is complete, the idea is to then reduce the time it takes for the value added activities and eliminate the waste from the non-value added activities. And these wastes can be characterised by the 7 wastes. So the first one is overproduction. This is to produce sooner, faster, or in greater quantities than the customer demands. The second one is inventory. This is the raw material, work in progress, or finished goods which is not having any value added to it, such as the one that we saw previously. Then we've got waiting, people or parts that wait for work cycle to be completed. Then we've got motion, so unnecessary movement of people, parts or machines within a process. Then we have transportation, so this could be unnecessary movement of people, parts between processes. And then we've got rework, so if you don't get the part right the first time, then there's a repetition or a correction of the process. And then you have over-processing, which is to process a part beyond the standard that's required by the customer. Then finally we have the last one, which is the 8th waste, or is the wasted potential of people. And in order to identify one of these 7 or 8 wastes, you often ask a series of questions. So the 5 W's and 2 H's is a good technique to do this. So we'd ask who, so who performs the process and who's affected by the process. We then might ask what's the purpose of the process and what are the steps in the process and what sequence should the steps take. Maybe the process has changed over time and you don't have to complete them in that sequence anymore. Then what does the process accomplish? Is it doing the job that it's trying to do? And what could be done better and what could be done differently? And mainly what purpose does it serve? We then have the when. So when do the activities take place? When should the activities take place? And when is the right time for the activities to take place? We've then got where. So where does the activity take place? And where does it need to take place? And then finally we've got why. So why does the company need this process? And why is this process important and why must it be done? As I mentioned before, processes evolve over time and sometimes processes that aren't required are nested within these other processes, and they often get overlooked. We then have the two H's. So the hows. So how does this process relate to other company processes, for example? And how is the work being done? And how could it be done differently, maybe using some Industry 4 technologies? And how can it be changed to match or exceed the best? And you can do this by an exercise of benchmarking. And then how will the results get measured? Is it KPIs or other sorts of metrics? The final H is how much. And this is related to how much does the old method cost and what will the new method cost. And this is key to create an effective business case. So when you've used these previously described methods, you then end up creating what's called a future value stream map. And this indicates the improvements that you've done. So as you can see on the left, where before we had 5.2 days, if it's sat around in the inventory, we now have 0 days. So the deliveries have now been delivered just in time, which is reducing that waste of inventory being sat around with no value being added to it. So the raw materials are now delivered daily. This eliminates inventory waste and increases the future process efficiency from 0.76% to 2.03%. And it's important to note that the value creation time never actually is equal to the cycle time. So what's the reason behind creating a current state activity map and then a future state activity map and then a value stream map that shows all the improvements? Because ultimately you're trying to create the best process. And once the non-value added activities are removed and the necessary but non-value added activities are reduced, it's critical that you revisit the value added process steps and check to see whether there are better ways to do the same work. And often we can use Industry 4 tools and technologies to try and achieve this. The "we've always done it that way" mentality can just as easily carry over to the value added activities as it did to the whole process. And determining the best practices enables an effective organisation to eliminate poor work methods, out-of-date practices, wasteful activities and unnecessary steps. And doing so makes the organisation highly competitive. So as I mentioned previously, with our current process map now complete, we can use this information to model a 3D discrete event simulation of a manufacturing process. As you can see, we can add machines to our model in order to monitor things like the utilisation, waiting times, and we can even schedule the uncertainty of breakdowns. Beginning from the left, you can see the blue squares, which are the sources of all the raw materials required to assemble the insulated van panels. These can also be configured for scheduled or just-in-time deliveries, for example, and then the materials follow a predetermined route throughout the process. We then have a wood saw at the bottom, then a GRP saw further up, then a styrene cutting saw, which will all prepare the materials ready for assembly and modification. The styrene is then combined into the vacuum press, which then forms the insulated panels to be later modified by CNC machines. The dark squares represent buffer stores, where the material is either waiting to be processed or partially completed parts are stored until other machines further down the line are free to work on the parts. The blue squares with the red arrows at the bottom of the screen are the sinks of the simulation, where finished products finally exit the system. Within this very manual process, you can see that we also have moving entities such as people and a forklift truck. This is where 3D simulation can be used to model and observe the various routes that people can take in and around other machines, which can be useful for showing the existing interaction of people within a manufacturing process. As you can see, at the early stages of the process, there is a potential violation of social distancing rules, where the saw operators are frequently coming into contact with each other and the vacuum press operator, which will clearly need to be addressed to comply with government guidelines for social distancing within the workplace. So, taking into consideration process improvement, we can redesign the system so that we've now got 2 vacuum press beds and we've got a 6-degree of freedom robotic arc positioned in the middle, which can easily access both press beds and even pick up raw materials without having to rely on human manual labour. As you can see, the human operators are much more sparsely situated and very rarely come into contact or break the 2-metre social distancing rule. So we've actually achieved an improvement of flow on the operation efficiency. We've managed to reduce the transport times between machines and inspection. is now automated. Hold the buffer stores are also more adequately positioned. And we've eliminated a lot of the waiting time or delays within the process. So that was just an example of how robotics can help, but there's other technologies out there that can also help you increase your process cycle efficiency value, which can then be measured by completing a future process activity map or a value stream map and justify the improvements in terms of the value added. So say you wanted to improve the value-added operations within your process, you could use things like open source data acquisition using the BrainBox Neural Edge Industrial Controller, the BB400 on the right, or maybe Tascom's proprietary plant run production monitoring system on the left. But before improving those value-added operations, it's good practice to focus on the non-value-added operations. And these include everything that we looked at from the 7 ways, so things like transport. So you could use Omron's Autonomous Intelligent Vehicles, or AIV, platform, which is able to use natural feature navigation to go around your factory, pick up parts, deliver them to where they need to be, all without human intervention. It increases throughput, reduces dwell time, eliminates errors, and also improves the traceability of parts throughout your manufacturing process. Or you might choose to use something like Ocado's robot swarms on the right that pack your shopping, and they can travel pretty fast, zipping around an area of several football pitches, picking your groceries and collecting them, so that that moving time or transport time is reduced for the human operator, which eventually stands and picks the items out of the boxes and then packs them into your bag for your shopping. For improving inspection, we can use technologies such as Faro's 3D data capture technologies, where we have everything from coordinate measurement machines to colour 3D scanners to laser trackers and laser projection systems for guided assembly. Then on the right, we also have the Mdt Robot, which stands for non-destructive testing, which is able to fully automate the testing process and transport of lifting parts from a pallet onto a testing bed, performing the appropriate tests, and then putting the parts back on the conveyor belt if it's passed the test. Then to improve the hold or storage, you can use technologies such as the AMRC's Pick by Light reconfigurable storage system, which you can see on the left, which highlights whether you've picked parts from the appropriate place or not by red or green indication of LEDs. Then on the right you have smart stock replenishment systems, which can either have weighing scales underneath or other methods to count how much stock is left, so you can automatically reorder parts when needed. Then you want to reduce those delays, whether it be in your supply chain using software such as iCluster, or maybe in your actual factory floor, your condition monitoring and predictive maintenance of very important motors that you might have in your production. This can be done via using things like the BrainBox that we saw before, in conjunction with various sensors that are all sending the data up to the cloud, so you can have a constant view of the health, and predictive maintenance can be then implemented on the data analytics side of things. And finally, you may want to reduce some of those setup times, maybe by using collaborative robots, such as the video you can see playing on the left. Or you might want to use other types of simulation software, such as CNC simulation software on the right, in order to try and predict how much time can be saved by doing a batch run of components rather than single piece flow. So in summary, a process map is a collection of data defining the borders of the process, illustrated by a high-level flowchart diagram. You then have discrete event simulation, which can be useful to simulate and compare multiple scenarios if enough data is collected to program the simulation accurately and the benefit outweighs the cost. And then a process activity map is a detailed mapping involving many value-added and non-value-added steps, which could be a table or a spreadsheet. And then a value stream map creates a summary diagram of the information and material flows within the lead time ladder, to clearly indicating where the time is lost to value or non-value added activities. And finally, some technology improvements, which we've just seen, can be implemented to help increase productivity whilst also ensuring social distancing procedures are adhered to.